Good day, and thank you for the opportunity to present. This project is the Valterra Termite Infestation Roof Replacement Program, located along the N11 corridor, serving residential housing associated with Valterra Platinum Mine. The project was nominated by MITEC in the light steel frame building and roofing category. Mining operations in South Africa typically provide employee and community housing, are responsible for the maintenance and long-term habitability of that housing, and they operate under the social and labor plan obligations. This plan prioritizes local employment, skills development, community upliftment, and housing upgrades are therefore not cosmetic, they are part of the operational continuity. They affect worker safety, stability, and most of all, dignity. They reduce long-term operational and maintenance risk. I am Nesh, Commercial Director of MITEC. My colleague Tseho, Business Development Manager, is also joining on the presentation today. The client for this project is Valterra Platinum Mines, focusing on how an engineered light gauge steel roof system was used to solve a systemic failure in a mining community at scale, with strong emphasis on strong constructability, quality assurance, and community involvement. Today, we are focusing on how the ultra-span light gauge steel roof system was used to solve the failure in this mining community, and the failure was caused through termite infestation. It's around community involvement. This project didn't start with an architectural ambition. It actually started with a failure. The mine is located in the termite belt, and over time, the timber roof structures in the residential villages were being systematically destroyed. Homes were no longer safer, and residents were living under roofs they didn't trust. The project itself started 4 years ago. The brief from Valterra Mines was therefore very clear. They said, create a roofing system that termites could never compromise again, that would work with existing houses, that could be rolled out at scale without specialist contractors or heavy equipment. Just as important, the mine wanted the solution to give back to the communities it operates in. Materials needed to be locally sourced or manufactured, and the construction method had to allow local people to be trained, employed, and empowered to build the solution themselves. Steel was essential in meeting this brief. The light gauge ultra-span steel truss system is a termite-proof lightweight system, repeatable and fully engineered. It allowed us to restore the safety to homes, create jobs, and deliver a long-term solution that is both technically sound and socially responsible. This is not a project about architectural form. It's a project about engineering resilience, community upliftment, and doing the right thing and doing it at scale. The project started 4 years ago, but for the purpose of this enrollment on the Steel Frame Awards, this project completion date was the 31st of December 2025. The total cost of the project was just over 77 million rand, and the roof structure was light steel frame. The feature of the structure was durability in the sector of mining. The project demonstrates how the light steel framing system can be used not just for new construction, but as a strategic refurbishment tool. The core challenge was not designing a new building, it was retrofitting a fully engineered roof system onto existing masonry houses of varying ages and conditions, many of which were never designed to support modern replacement structures. The solution had to restore safety and compliance without increasing loads and without changing the visual character of the homes. From an engineering perspective, this is where the advantage of lightweight, high-strength steel trusses becomes critical. They allow structural performance to be achieved efficiently while remaining compatible with the existing walls and foundations. What makes this approach distinctive is that it is not a simple substitution for timber. It is a software engineered structural solution. Using Mytek's Premier platform, each roof is designed digitally, including layout, member sizing, bracing, and connections, ensuring that every installation meets current design codes, even across varying houses. That engineering intelligence is built into the system itself, which allows the project to achieve consistency, traceability, and repeatability across hundreds of installations. The key strength is the ability to deliver the project at scale without losing engineering control. Standardized detailing, controlled component supply, and defined inspection processes, ensuring at the same time the level of quality is maintained from the first house to the last. Importantly, by resolving complexity upfront in the design and system, the on-site process remains structured and reliable. There is a clear separation here between performance and appearance. Ultimately, the significance of this project lies in demonstrating that engineered-led refurbishment can outperform traditional replacement cycles associated with timber roofs. It positions steel as a material capable of delivering quiet, repeatable transformation, not through form, but through durability, precision, and long-term value. What's particularly important here is that the engineered system enabled a construction methodology that is scalable and repeatable, while still being suitable for execution by trained local teams. This ensured that the same technical solution could be delivered consistently across this large housing program without compromising quality or compliance. The completion of the work, like I said, was December 2025. The cost of the UltraSpan roofing system for that period was 45 million, of a tonnage of just under 490 tons. The maximum spans on the site, although varied, was 10 meters, and trusses could go up to 2 meters in height. The roof cladding system with concrete roof tiles. The main structural engineer and roofing contractor for this project was Giant Engineering, and the fabricator being Mytek. The roof structure consists of UltraSpan trusses installed directly onto the existing masonry houses. These steel trusses replace the original termite-damaged timber roofs while retaining the existing walls and foundations. From an engineering perspective, this is critical because the solution had to provide a complete structural upgrade without introducing additional load onto structures that were not designed for heavier systems. The trusses are manufactured from high-strength, thin-gauge galvanized steel and supplied as components that are assembled and erected on site. It allows us to deliver a fully engineered structural solution. Building on the structural system overview, here we explain how the roof structure performs in terms of load transfer and stability, including self-weight, roof tiles, and wind actions. Termites, although being the systemic problem of the previous roofs, were not the only problems. There were failures in the roof coverings and the roof installation and compliance as well. What makes UltraSpan the framing solution that was technically notable? It was not the form, but the way the engineering is embedded into the system and delivered at scale. The use of this software engineered light gauge system allows us to deliver consistent code compliant roof structures across a large number of existing houses. All the engineering complexity, including the member sizing, bracing, and connections, is resolved digitally upfront. This is important because it means that by the time the system reaches the site, the solution is already defined, coordinated, and validated. As a result, installation becomes a process of executing a control system rather than interpreting drawings or making adjustments on site. What's particularly significant in this project is that the real challenge was not the architectural complexity, but really the scale and the constraint that the site had to offer. We are working across termite damaged houses with variations in existing structures, limited access, community based labor. The framing system therefore had to be robust, repeatable, and tolerant of real world conditions, and still deliver full compliance. From an efficiency perspective, the system is optimized using the Premier platform. The connection detailing and the fastening of the roofing system is also designed through the Premier software program, and it became a process of executing this controlled like a system rather than interpreting the drawings. Quantities were also calculated phase by phase, which reinforce a disciplined, non-generic approach to design. So while the images show a relatively simple structural form, what they actually represent is a highly controlled, optimized engineering system designed to perform reliably across many installations and not just one. The digital platform specifically on this role of digital engineering in the project. The structural system itself is designed using Mitek's Premier platform, which integrates a layout structural design, code compliance into a single environment. The key point is not the software itself, but that it consolidates engineering decisions upfront, ensuring that every roof is fully resolved before it reaches the site. Beyond design, the BIM and 3D modeling we use primarily as coordination tools rather than for complex modeling. In this project, digital tools were not used to create form, but to control risk, quality, and repeatability. The combination of system-based engineering and BIM support enabled the refurbishment program to be delivered reliably by community-based teams, with confidence that every roof installed matched the engineered intent. The roof layouts and bearing positions, bracing strategies were all clearly defined in the model, allowing all parties to understand how the system fits together before fabrication and installation. This meant that potential issues were addressed digitally rather than being discovered during erection, which was critical in a phase that involves community employment. Another important advantage was the ability to manage the size of the project, and as the project progressed through phases and the number of houses per phase were confirmed, the system allowed quantities, spans, and tonnage to be recalculated efficiently without redesigning the entire solution. This ensured that engineering consistency and optimization were maintained across the entire program. So in the project, digital engineering was not used to create complexity. It was used to reduce risk, maintain control, and enable consistent delivery at scale. At this point, I'd like to invite the members of the panel to take out your phone and scan the QR code to have access to the Mitek 3D viewing of one of the houses in the Valterra project. The fabrication was done by Mitek. Mitek is situated in Midrand, and the roof truss system is manufactured and fabricated per size, per length, and pre-cut, pre-punched, and pre-labeled to be sent out to site in accordance with the Premier design. Rather than bespoke workshop fabrication, the project deliberately places complexity upstream in the engineering and system definition. This approach to fabrication outputs are predictable, traceable, and installation ready, forming the foundation for controlled on-site assembly without compromising structural intent. The ultraspan light gauge system takes fabrication from a production facility and takes it onto site, extending the fabrication to site. The precision of the ultraspan system, cut-to-length members, printed labeling, and layout-matched kits enabled fabrication logic to be carried through directly into site truss assembly. The local communities on these projects had no prior experience in the roof truss erection, and 4 years ago, there were individuals that were taught how to read the members, how to read the plan, how to receive the delivery and sort a delivery. 4 years later, there are teams of installation putting up roofs on this project, and the capability was built over time. Even the complexity of the roof installations has improved in the teams. According to Giant Engineering, the supervision and the compliance on this project, the on-site truss assembly and erection was carried out by the trained community teams under continuous professional supervision of Giant Engineering. Their supervision ensured the correct interpretation of the engineered layout and the proper sequencing of the truss design, also ensuring full SAISC compliance. They managed risk and maintained quality. But the beauty of the ultraspan light gauge system and the steel system as a solution on the site meant that it became a very teachable system and ensured that erection remained consistent, repeatable, and compliant. Around 6 to 7 kgs per square meter on the Valterra site is what the loads were for the ultraspan roofs. On an 18-ton truck, they could carry between 2,500 to 3,500 square meters, which equivalent to 25 to 30 houses per delivery. This reduced the delivery logistics drastically. It's a crane-free installation. There's safer manual handling. There's fewer deliveries into remote communities. In this context, reduced weight is not a logistical advantage. It is the engineering enabler that makes compliant, crane-free erection possible at scale. Here we're demonstrating the size of this project. We continuously use the word scale for the Valterra project, and it's existing homes that had to be refurbished and roofing replaced. So far, the project is running for 4 years and is pitched to run for another 3 consecutive years. Key delivery challenges was the project was defined by the need to deliver a technically compliant roof replacement program under conditions where conventional construction controls were not available. They were previously unskilled community teams. They had to be trained in logistics and sequencing and how to read layouts and drawings. And there was a fixed 2-week rehousing window in which a family were removed from the home home had to be refurbished, a roof had to be put on, and the family rehomed. Maintaining all of this coordination was part of the site constraint, but having an easy teachable system like the light gauge roofing system of ultrasan, these constraints were managed through the project. How these challenges were resolved, and it came from the fabrication. It came with the pre-cut delivery. It came with the pre-measured components, pre-labeled components. And it came with a system that needed to be erected on site without much adjustments. For the project, why steel was essential, it is durable and it became the refurbishment solution that met the brief, which was to have a termite free solution, a permanent termite free solution. Its high strength to weight performance, engineering precision, repeatability at scale, reduced life cycle maintenance. Steel allowed structural performance to be upgraded without altering the external appearance of the homes, delivering long term reliability rather than architectural change. Quality starts at the MyTech Midrand facility. Quality, sustainability, and efficiency on this project was driven through a factory controlled fabrication at MyTech. MyTech has an integrated management system certified to ISO 9001, ISO 14001, and ISO 45001. Ultraspan components were cut to length, inspected, pre-labeled, and approved. MyTech site drawings were sent out with each roof. Bundling of the projects per house, allowing for ease of logistics and sequencing on site. The use of the MyTech blue text screw made for easy, immediate visual confirmation of correct fastener installation, simplifying site inspections. All engineered details were explicitly documented, and roofing inspections were carried out by Giant Engineering. What we're proud of on this project, it was not so much the pride of us as a fabricator or Giant Engineering, it was the pride of each individual in one of those homes. The homes that they stayed in before Ultraspan light gauge steel roofing system was used, and the homes that they now live in, knowing that they are safe and their families are safe under the roofs that was provided. The significance of this project lies in how engineering decisions translate into social outcomes. By investing in a fully engineered steel roof system, Valterra addressed a systematic failure in its housing stock, while simultaneously enabling local skills development and consistent delivery. In this case, community impact is not a separate initiative, it is the direct result of disciplined engineering. Thank you.